Hello and welcome to the new video of YouTube channel Tech Guru Gautam Prasad. This is Basics of Electrical Engineering Part 3. So in this part of the video, we will discuss passive components of the AC circuit. In the passive components of the AC circuit, we will discuss resistors, capacitors and inductors and their behavior in AC circuits. They're called passive circuits or passive components because they consume power and they do not amplify the signal or they do not act on the signal in any way. So as far as frequency is concerned, frequency remains the same passing through these three components and they all consume power in some way or the other. So we will see how do they behave differently in AC and DC circuits. We will focus on AC's behavior of these components. In the case of AC, their behavior we will focus on. And these passive components, as I told you, they consume power and cannot increase or amplify the signal. Passive components used in electrical circuits can be connected in infinite number of ways. There could be several number of ways or fashion in which they can be connected. Here is a particular way. This Vs is the source of alternating current and this is causing Is in the circuit. Is is the current caused in the circuit because of that source voltage Vs. XL and XC are basically reactances. They are reactances in the circuit. XL is the inductive reactance, whereas XC is the capacitive reactance of the circuit. And these two things depend on the frequency. Unlike resistance does not depend on the frequency of electrical signal in the case of AC. But these two things, XC and XL, depend on the frequency. Later we will see how they depend on the frequency. But for here, let's understand reactance depends on frequency. Now reactance is represented by X because till late, these things, uh, resistors and capacitors were causing impedance on the path of electrical current, but uh, they were not known how and why it is causing or affecting the flow of current in such a manner. So they were named X, and it is of course measured in uh, ohms as your resistance is measured. So resistors has a fixed value, whereas these XC and XL have a variable value because they depend on the frequency. Note that theoretically, perfect or the pure capacitor or inductor does not have any resistance, but practically, you will see certain amount, finite amount of resistance will always be associated with, you know, inductor and capacitor. Okay, so purely, inductive or capacitive could be little imaginary sort of thing. Now let's understand how purely resistive circuit behaves in AC. So resistance is measured in ohms, and resistors cannot be can be of fixed value or variable value in the circuit. Here we have taken a fixed value of resistance R, and Vs is the source of alternating current, and it is causing current Is in the circuit. Uh, IR is the value of, as it has been shown here, IR. IR is the value of current passing through this resistor. And VR is the voltage drop across this resistor. So these are the terminologies that have been used. That's why I am explaining it here. So the value of Z is nothing but impedance, is equal to VR, that is voltage across the resistor divided by current through the resistor. And that is nothing but the value of resistor. So impedance, complete total impedance in the circuit is equal to the value of the resistance. And Z can also be represented as angle 0 degree equal to sum of resistance plus J is the imaginary component, that is the reactive component, and that is reactive component is 0 in this case. There is no reactive component. And that 0 degree means the phase angle between current and the voltage here is 0 degree. That means there is no phase difference between the voltage and the current in this type of resistive circuit or purely resistive circuit. Uh, in the case of purely capacitive circuit, let's see how will be the behavior. So capacitor, the component, this is a component that has ability or the capacity to store electrical energy, okay, uh, like a battery does. The capacitance value of the capacitor is measured in farad. So this is important. Please remember this fact that it is measured in capacitance of the capacitor is measured in farad and it is denoted by F. Okay. Uh, at DC, a capacitor has infinite or open circuit impedance. So when it is used in capacitor is used in DC, it behaves as if there is a open circuit. Okay. And XC, that is capacitive reactance, uh, while at very high frequency of the capacitor has zero impedance, short circuit. So at very high frequency, this behaves as a short circuit. Means there is uh, uh, no resistance. Okay. So here there is no resistance, means the value of resistance is zero. Xc is equal to the voltage across the capacitor divided by current through the capacitor, and that is equal to 1 upon 2 pi Fc. Z is the value of total impedance of the circuit, and this is minus 90 degree because the voltage, lags here with respect to your current. In other words, your current leads here uh, with respect to your voltage. So it is vice versa, but that has to be understood properly. Minus 90 means your voltage is lagging, not your current is lagging. So it is equal to 0. As I told you, this resistive component here is 0. There is no resistance in the circuit and it has only capacitive part. Capacitive part. So capacitive reactance part is present here in the form of Xc, that is causing you know impedance in the path of the electrical current, and Is, that is source current, is equal to Vs, source voltage, divided by the value of capacitive reactance. So that is it. So why it is said that it behaves like an open circuit in the case of DC. So having applied a DC voltage here, this capacitor will charge up to the source voltage, and then having charged as the positive plate in terms of positive voltage and negative plate in terms of negative voltage, the polarity appears across this capacitor and it stands as a battery itself against the battery it is having here. So the current stops to flow. No current will flow through this circuit in the case of DC, and it behaves like an open circuit. Whereas in the case of AC, at higher frequencies, if the frequency is high, look at this uh, equation, X is equal to 1 upon 2 pi Fc. So higher the value of Fc, little will be the value of, higher the value of F, little will be the value of Xc. So as your F is increasing, your Xc is decreasing. For a higher value, a smaller will be the value of Xc. So it is extremely low and almost negligible if your frequency is high. So that is what it was saying. Now let's try to understand purely inductive circuit. So in the case of inductive circuit, it DC inductor has zero impedance. That means short circuit, very uh, opposite to the behavior of the capacitor. While at high frequencies, inductor has infinite, that is open impedance. Again, just reverse of the capacitor. Okay, in the case of high frequencies, capacitor was behaving as if it is a short circuit, but here your inductor behaves as open circuit. Okay, so when it is put to the DC circuit, it has zero impedance in the circuit. That means it behaves as a short circuit. So if you will connect an inductor to the DC, your inductor will burn because of high current. There is no hindrance in the flow of the current, and that is why the entire energy will be dissipated in the inductor, and your inductor is ultimately going to burn. You can take solenoid as an inductor for better understanding. Now here in this circuit you can see there is an inductor named L, and Vs is the alternating source, and this is causing alternating current Is. So XL, this inductive reactance is equal to VL upon IL, and which is equal to 2 pi FL. Now, contrary to earlier case, the case of the capacitor, here if the frequency is increasing, the value of XL is increasing. So at higher frequencies, you can understand it will carry a higher value, and it will not let the current flow through the inductor. So uh, this behaves as an open circuit in the case of AC if the frequency is high. So Z is equal to plus 90 degree. That means voltage leads here. The current voltage leads here, not current leads here. Okay. So current lags by 90 degrees with respect to the voltage, and this is shown as zero because here also resistive component is zero for the purely inductive circuit. Pure inductor does not carry any resistance. It is supposed not to carry, but it is imaginary situation. In all practical situations, your coil or your solenoid or inductor will have certain value of resistance because wire carries some resistance. So, however small it is, it will carry that value of a small resistance. But here, because we have considered it to be, purely inductive circuit, we have taken this component resistance to be zero. So resistance to be zero and XL only inductive reactance is there, and source current is equal to source voltage divided by reactive component, uh, inductive reactance. Now let us consider a situation where all these three components have been used in series. Uh, Series AC circuit. Here only two components have been taken. I'm sorry. This resistor and capacitor have been put together in this AC circuit. So this in this case, what will be the impedance? The first question arises: what will be the impedance? As because it has resistance and capacitance both, so it will be equal to square root of R square plus XC square. So Z is equal to minus phi. That means here it will not, your voltage is not going to lag by 90 degree, but by certain angle between zero, which will be between 0 to 90 degree. So this phi is between 0 degree to 90 degree, any angle. So it is equal to R minus JXC. R minus Jx, and the value of phi, which is between minus 90 degree to 0 degree, is equal to tan inverse Xc minus Xc upon R. And Is, that is source current, is Vs upon Z, that is equal to Vs divided by square root of R square plus XC square. And Vs equal to square root of VR square plus VC square. Now let us consider the RL circuit where resistor and inductor, one resistor and inductor has been used in the AC circuit. Vs is the AC source, Is the current source current, and Z equal to this impedance is equal to a square root of R square plus XL square, and Z equal to plus phi. So your voltage is leading here. In this case, current is lagging, but voltage is leading. So by an angle plus phi. So R, the value of Z is R plus JXL, and phi is between 0 degree to 90 degree. And the value is equal to tan inverse XL upon R. Is, that is source current, is equal to source voltage divided by impedance, and that is equal to Vs upon square root of R square plus XL square. Vs is equal to Vs, that is source voltage, is equal to this is very important relationship. The source voltage is not the algebraic sum, the straight algebraic sum of VR and VL, but it is a vector sum basically, and that is equal to a square root of VR square plus VL square. So Vs is the vector sum of VR and VL, and that is why here we have squared these two, and we have taken the square root of the sum. Here LC circuit. LC circuit is little different from RL circuit and RC circuit. Here both the components are, reactive, are not resistive. Okay, so L is uh, inductance and C is the capacitance. C is the capacitor, L is the inductor, and Z is the impedance, which has the value of the square root of XL minus XC whole square, and Z equal to XL minus XC or XC minus XL, whichever is greater. Basically, we deduct the other from that. So Z is equal to angle phi plus J and equal to 0 plus J XL minus JXC, the difference. Again, the resistive component has been considered 0 because here also we have taken pure inductance and pure capacitance. So that is why reactive component, resistive component in this case also, this resistive part is 0. As I am indicating by pointer, this part is 0. And Fr is equal to 1 upon 2 pi square root of LC. At Fr, that is a resonant frequency. This is a frequency where, the value of XL and XC become equal. And very peculiar thing happens when XL and XC are equal, you can see the value of Z becomes 0. So this is a situation where the current will be maximum. It will, because there is no impedance to the circuit. The Z value of Z is becoming 0 basically. So there is no hindrance in the flow of the current. There is no, impedance in the flow of the current. It is flowing without any resistance basically. There is no resistance on the path of the flow of the current. So unopposed current flows in the circuit, and this is called resonance. So the resonant frequency is equal to 1 upon 2 pi square root of LC, and at resonant frequency XL equal to XC, and VL is also equal to VC. Both the voltages become equal and opposite, and they cancel each other, and that is why this net voltage across these two components L and C becomes 0. In this case, Is equal to IL equal to IC, because they are in series. Is the IL is the current through the inductor, and IC is the current through the capacitor, and Is the source current. So all these three become equal because they are in series. All right.